Hi everybody, hi, Mike here. Today we're going to talk about solubility product. Remember this good old chart of Ka's and KB's? I want you to get out your handout and I want you to do this. Flip it over to where we have values for solubility product constants. What are those? Well, I'm about to tell you right now. Solubility product is called KSP, not KAKB. Now we're KSP, stands for solubility product. Let's take something simple. I'm going to pick out of your chart silver chloride, solid. Now, the trick of using an equilibrium constant is to know what it represents. So with Ka, that's the process of something reacting with water to produce H3O+. A Kb would be the process of something reacting with water to produce OH-. This is for very sparingly soluble salts. So we have to write the reaction of it dissolving in water. So back to Gen Chem 1. You know, chlorides are +1. That means that's silver plus, Cl minus. And so we're going to write a K of that. However, unlike the Ks with acids and bases, there's no denominator. It's a product. Why is there no denominator? Well, that's because a solid does not change its number of moles per liter and is a constant. So we'll talk about that in just a second. But anything that's a concentration can. So we include that. There's no denominator, as we said, and that product of silver plus concentration times the Cl minus concentration, looking in your table, is 1.7 times 10 to the minus 10. All right, let's talk about why something doesn't go in the denominator with KSP. Oh, check it out, there's my cat. You missed him. Okay, never mind. Let's say that's a beaker of water. I'm going to put some AgCl solid in there. It's going to look like it ain't going to dissolve, but I'll tell you what, the fact is that all those values in your table are not zero. They're a number, so they all do dissolve a little bit. So a lot of the silver chloride would go to the bottom because it's denser than water. But you would have in the solution a tiny amount of silver plus and a tiny amount of chloride. Now, and then we'd use this expression. We'd know that that concentration, no matter what the circumstances, would have to be a product of 1.7 times 10 to the minus 10. Not more, not less. Actually, you could have less if it all didn't dissolve, which would be really, really not much stuff at all. So let's pretend I just dump more in. Okay, I put some in, and then I go and put some more in. What's going to happen? It's just going to go to the bottom. And the number of moles per liter here are not going to change. I just added more moles and more liters. So this is a constant, and this is a constant. And so at equilibrium, where you're past the saturation point, all these things are constants, and they can be used to solve problems. So let's talk about how we do solve problems. All right. Let's say we were going to go and try to find out what these two were. We could say this is minus x, right? Every bit of that dissolves, that'd be minus x. We could call that plus x. And so this would just simply be equal to x times x, which is just x squared. So if I got past the saturation point, x would be the square root of 1.7 times 10 to the minus 10. No ICE chart, no 100 times rule, these things end up boiling down to be very simple problems to solve. Let's go find x by taking a square root. All right, the square root of 1.7 times 10 to the minus 10 is 1.3 times 10 to the minus 5. And so that means that the number of moles per liter of this that dissolve is 1.30 times 10 to the minus 5. And the concentration of these are 1.30 times 10 to the minus 5. All right, and 1.30 times 10 to the minus 5. So back to our little thought experiment. If I just took any amount of water, doesn't even matter, I just saturate it, I would know that both these concentrations would be a constant at 1.30 times 10 to the minus 5. That would be, of course, at 25 degrees C. If I change the temperature, you guys know all about that. That would, of course, shift the equilibrium. All right, and then you could dump in as much as you wanted, just go straight to the bottom, and those concentrations of silver and chloride would be fixed at 1.30 times 10 to the minus 5. Okay, now let's talk about another example. What if we were talking about calcium fluoride? All right, calcium fluoride, when it dissolves in water, makes calcium 2 plus ion and 2 fluoride ions. And so we would set the Ksp up like any other K, where we say products over reactants, but we don't put the solid in there. So Ksp is the concentration of calcium ion to the power of its coefficient, that's to the first power, times the fluoride ion concentration squared. See the difference there because of that coefficient of 2. So it turns out that this salt breaks into 3 pieces, where others break into 2, or they all vary based on their formula. And so if we look this up, this is 3.9 times 10 to the minus 11. According to your chart. I found that in your chart. Right in there, they're grouped by what the negative ions are. So you'll see at the top left corner, it says fluorides. Okay, so this is minus x. This is plus x. This is plus 2x. So this particular one would be x times 2x squared equals 3.9 times 10 to the minus 11. Now, we're breaking into some new stuff, so I'm going to take it easy on you guys. Next time, I want to hear what you say x is when you solve for it, and we'll talk about how to use that number. All right? See you next time. I'm going to go try to go slow with this new stuff without your faces there. So give it a shot, find x, and then let's talk about our next example, by the way. Give you a little sneak peek. And I'll give you another little thing to think about. So find x, and then we'll put our answer down there. Next time, write Ksp expression for. Let's take one that's kind of goofy, guys. I'm going to take one that's a little bit even more weird. All right, let's take aluminum hydroxide. That's in your chart too. Write the Ksp expression for that, and then also find x. X tells you a lot. Tells you how many moles per liter of everything that's going to dissolve. And we'll solve problems with that. So that's for next time. I want you to work on that. Stay healthy, guys. Bye.